Hello and welcome, SFU Math 232. My name is Brenda. Today we're going to take a look at section 7.2, Properties of Bases. So we're going to start this lecture just with an example so we can see what can happen and when it doesn't happen. So here we have a vector W, and we're going to express it as a linear combination of V1, V2, and V3. So what we want to be, what does that mean? That means we want to be able to take the vector 0, 4, 3 and write it as a linear combination of the other three vectors, V1, V2, and V3. Okay, so in order to do that, what we do is we put the the vectors into a augmented matrix, and we solve for the value, this one over here, which we would, if we were like writing this as ax equals b, this would be the b. In this case, it's a w, and we're put the vectors in here as columns. Okay, and then we're going to row reduce this. So I think because of that row of zeros, I'm going to put that immediately to the bottom, and I'm going to put the row with where there's a 2 here in the first pivot position. I'm going to move that to the top. So a couple of row interchanges to get to this place here. Like that, and then let's see, I'm going to divide the first row through by 1. Sorry, I'm going to divide the first row through by 2 in order to put the 1 into that position right there. Okay, and at this point I can see what the values of the constant circuit C1, C2, and C3 are going to have to be. What that is that C3 is free. C2 is 3 minus 2C3, and C1 is 2 minus C3. So I'm going to let C3 be T, and then I will write this like this. C1, C2, C3 equal to 2, 3, 0 plus T times minus 1, minus 2, and 1. Okay, so you can see that it's not going to be unique. So for example, if I chose T to be equal to 0, let's just do that. T equals 0, then just make that choice. Then I would see that C1, C2, and C3 would be equal to 2, 3, and 0. And then that would tell me that I would be able to write V3 as, well, what is V3? V3 is 0 to 2. Well, that's not what I want to show, actually. Hang on a second. I do want to show you that, but I want to wait in a sec here. If I did this would, if I got C1 equals to 2, C2 equals to 3, and C3 equals to 0, that means something hasn't gone wrong. I should be able to write W as 2 times V1, 0, 2, 0, plus 3 times V2, and plus no times C3. So does that equal to W? I sure hope so. 0, 4, 3. So I have 2 times 0 plus 3 times 0 is 0. That worked out. 2 times 2 plus 3 times 0 is 4. That worked out. 2 times 0 is 0 plus 3 times 1 is 3. So that worked out. So I could pick that. I could also choose, for example, T equals to 1. So I could also do that. I could choose T is equal to 1, and I would then form constants C1, C2, C3 as 1, 1, 1. Okay, and that should also work. So I should then be able to write W as 1 times 0, 2, 0 plus 1 times 0, 0, 1 plus 1 times, what is that last one? 0, 2, 2. That should still be, again, equal to 0, 4, 3. So let's see, that's zeros in the first. 2 plus 2 is 4, and 1 plus 2 is 3. Yes, it worked. So that worked as well. So I've now expressed W as a linear combination of V1, V2, and V3 in two different ways. Now, we'll notice what I wanted to show you before, and I'm just going to point this out right now. We'll notice that V3, which is this guy here, 0, 2, 2, is equal to V1 plus 2V2. Okay, that is, let us just write that out. That is 0, 2, 0 plus 2 times 0, 0, 1. That gives you 0, 2, 2. Okay, so we see that V3 can be written as a linear combination of V1 and V2. That means that V1, V2, and V3 are not linearly independent. Okay, so now let's get the theorem here. The theorem is that if we have a set of vectors B, and if the set is a basis for the subspace, then every vector W can be expressed in exactly one way as a linear combination. Now, we didn't see it being expressed in exactly one way above, and that's precisely because V1, V2, and V3 are not a basis, because V3 is linearly dependent upon V1 and V2. Okay, so we saw an example just above of it not working. It's not unique, and we know the reason for it not being unique. It's this thing here, that they were not linearly independent. Okay, so let us just recall what it means. Basis. It means that it spans V, and the vectors are linearly independent. And that's the one we were missing above. Okay, so let us just prove this. So the idea is, if we have a basis, then when we pick a vector in the subspace, it can only be written in one way as a linear combination of the vectors that form the basis. Okay, so let's write out a proof for this. A B is a basis. We are given that. For V. That tells you then that B spans V. Now what we're going to do is we're going to take a vector W, take W in V. We can write W as a linear combination of the vectors I'm writing W as a linear combination of these vectors here. Okay, what I want to show, that this is equal to W. What I want to show is that that's the only way. There's only one set of constants, C1, C2, all the way to CK, that makes this true. So let us consider that there is another way. Let me just write out what that would be. That would be then C1 prime V1 plus C2 prime V2 plus dot 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 plus CK prime VK, also equal to W. So we have that, we have now sort of said, okay, we're guaranteed that there's one way to do this. Perhaps there's a second way. Now what I want to show is, of course, that each one of these constants here are exactly the same as these constants, which means that there is only one unique way of doing that. Okay, so now let us take these two expressions for W and subtract. So I'm going to take this guy here, and subtract this guy here on both sides. So I have w minus w on this side, giving me 0 on the right-hand side. And then on the other side, the subtraction yields this. So I am subtracting. And the subtraction yields C1 minus C1 prime V1 plus dot 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 plus CK minus CK prime VK, and that is equal to 0. However, we know that V1 through VK are linearly independent. That's because they form because B is a basis. Okay. So we use the first thing that we get out of B being a basis, that it spans V, and then we use the second thing that we get from B being a basis, that is the vectors are linearly independent. Okay, so that means that each one of these things has to be equal to 0. It means that C1 minus C1 prime must be 0, and CK minus CK prime must be 0 for this sum to be 0. And that, of course, means that for all of them too. It's not just the two. It's for every single one of these constants. And so that means that C1 is equal to C1 prime, C2 is equal to C2 prime, etc. All the way down, CK is equal to CK prime. And that means actually, in fact, that this guy right here is the same as this guy here because those constants are equal. So in fact, there's only one way of expressing W as a linear combination. Therefore, W is expressible in exactly one way as a linear combination of the vectors of B. That is because B is a basis. Okay, so now we imagine we have a set of vectors and they may not form a basis. What do we do in order to adjust the set to make them into a basis? Okay, so this theorem is going to basically tell us how we can do that. We're just going to talk about it a little bit. So if we have a finite set of vectors, that's going to be called S, and we have a non-zero subspace V. If S spans V but is not a basis, then what you can do is remove appropriate vectors, and then you will end up with S still spanning V and S being linearly independent. Because if it spans V, but it's not a basis, that means the vectors in S are linearly dependent. Okay, and then we go on the other side. If we've got a linearly independent set, but it's not a basis for B, so that means it doesn't span V, then what we do is we add vectors to it such that we are then capable of spanning. Okay, let us just write out just a little bit of explanation about this. So let's just talk about A a little bit. We have that S spans V, but is not a basis. It's not a basis. Okay, what do we know about bases? They have to be span and they have to be linearly independent. Okay, so we know that S spans, so we know that we have an issue with this guy. That means that we can then conclude that some vectors, more than one, no, not more than one or more, some vector in S is linearly dependent on the others. Okay, they or it, depending how many there are, can be removed. The removal will not affect the span. Say, for example, we identify in our set of vectors that compose S. Say we find that V3 is some linear combination of V1 and V4. Okay, we've got K vectors in there, and so S is the set of vectors. Is this set of vectors here, V1 through Vk. Okay, so if we had a vector W, we would be able to write it like this. W being in the span of S, we would write W like this, all the way up to like that. And then we would note that what we could do is take W, we would keep the like C1 V1, and then we would have still C2 V2, and then C3. But then now when we got to V3, we would simply replace V3 here with 2V1 plus V4. And then we would keep going. C4, V4, and we would just keep going till we got to the end. CK, VK. Okay, then of course we can combine the two C3 with the C1, and we can combine the let's see, C3 again with the C4. And we can rewrite, and we would then be able to express W in this way here as C1 plus 2C3 V1 plus C2 V2 plus C3 plus C4 V4 plus dot dot dot, and then we would get to the end. Okay, so now we've taken W and we're able to write it as a combination of vectors, and we have not had to use the vector V3. So then we can eliminate V3 from S. So we would at this point now eliminate and we would keep doing this until we got down to a linearly independent set, at which point it would still be spanning, and we would then have the linear independence, and then we would have a basis. So that's the removing appropriate vectors. Okay, part B, what we do is we're told that S is linearly independent. Okay, and it's not a basis. So we immediately conclude from that that S does not span V. So this is sort of the other way around. It doesn't span V. So what do? You keep adding linearly independent vectors. That is, I'm going to keep adding a vector such that the vector I add is not dependent on any of the ones currently in S. Okay, and you keep doing that until it spans. And at that point, you have a basis. Okay, so that's what theorem 7.2.2 is telling us. Okay, let's take an example here. We have a space V, and the space is the span of these 4 vectors here. And we've got the 4 vectors listed there. We have 4 vectors, and you notice that these have 3 components. These vectors are in R3. So we have 4 vectors in R3. Okay, so for sure, we do not have linear independence. Okay, V1, V2, V3, and V4 cannot be linearly independent because we have 4 vectors and we are in R3, and the dimension of R3 is 3, and that is the number of vectors in the basis. So that this v here is these vectors v1 through v4 are not a basis for R3. Okay, so then I'm going to just look here, and I can see inspection here. I'm just taking a look at the vectors that I have, and I notice that 5/2 of 0, 2, 0 is equal to 0, 5, 0. So 0, 5, 0 is dependent upon 0, 2, 0. So so toss out 0, 5, 0. I don't get anything from that I can't already get from V1. So now I'm left here. V equals to the span of, and I've got 3 vectors left, 0, 2, 0. I've gotten rid of 0, 5, 0, and I've got 0, 2, 2, and I've got 0, 0, 1. Okay, so now it's actually possible that this is a basis, because it's possible, I'm not saying it is yet, in the sense that we see that there's 3 vectors in there, and it could potentially span R3, and then that would then it would be a basis, okay, because a number of vectors in there would match the dimension of the space, like if V is R3. However, I look at this, and it's in fact, I can see from looking at this example here, the vectors here, that 0, 2, 2 is dependent upon the other 2 in this manner. Okay, so that means I can toss out this guy too. 0, 2, 2. I don't get anything from having that one in. That guy there, 0, 2, 2, is dependent upon the other 2. Okay, so now I'm going to rewrite V again. V has not changed. It is the span of 0, 2, 0, 0, 0, 1. Now here I can easily see that these 2 vectors are linearly independent. One is not a multiple of the other. Okay, so let me just make note of that. 0, 2, 0 and 0, 0, 1 are linearly independent. Okay, and they span R2. So this thing here, 0, 2, 0, 0, 0, 1, this is a basis for R2. Okay. Well, and also we were supposed to here find a basis for V, and in fact this thing here is a basis for, it is a basis for R2, but it is also a basis for V. So we got told to do. So there is 2 linearly independent vectors, and they span R2. Basis for basis for V, which is the span of this. V is the span of these guys here. Okay, let's take another example here. Find a basis for R3 that contains these 2 vectors. Okay, so first thing I'm going to do is notice if these 2 vectors are linearly independent. So I notice that V1 is not equal to K times V2. So that means that V1 and V2 are linearly independent. If I am going to span R3, I am going to need 3 vectors. So I need what the problem now has become is to find some V3 in R3 such that V3 is not equal to a combination of V1 and V2. That's what I want to do. So one way to do that would be to take a look at the determinant of the matrix that contains V1 as the first column, V2 as the second column, and my soon-to-be V3 with components A, B, and C of the third vector. And I want that determinant to be non-zero. So I go ahead and I take that determinant, and I get this using a cofactor expansion along the first row there. I get this. And that gets me this guy here, minus C plus 2B minus A cannot be equal to 0. So any A, B, and C that satisfy this requirement will provide me with a third linearly independent vector. So you can pick a whole bunch of there's a whole bunch of choices here. For example, I could pick A is equal to 1, B is equal to 1, and C is equal to 2. That would be minus 2 plus 2 giving me 0, minus 1, that's minus 1. Okay, so that works. So then I can identify V3 as this guy here, 1, 1, 2. And I've now got three vectors, V1, V2, V3, which I know are linearly independent. There's three of them, so they are now a basis for R3, the three of them together. Okay, so if V is a non-zero subspace of Rn, then the dimension of V is the largest number of linearly independent vectors of V. And the dimension of V is the smallest number of vectors that span V. Okay, so I don't know, for example, if V is equal to the span of 1, 0, 0, 1, you can see that those are linearly independent. So the dimension of V is the largest number of linearly independent vectors. So the dimension of V is equal to 2. And in fact, you need two dimensions to, you need two vectors to span V. I mean, you cannot span V with one vector. So for example, the span, let me just take one of these vectors, 1, 0 is not equal to V. All right, we can take subspaces of subspaces. So if we have a subspace V, W is a subspace of V if there's two conditions met on it. It is itself a subspace of Rn, and it is a subset of V. Okay. So I mean, you can sort of, I don't know if, can I get a drawing of this? Yeah, let us say we have something that we're calling Rn, like that. And we have subspaces. We have a subspace that looks like that. Let's see, that is our subspace V. Okay, then we have W. It's inside here. Now, W has to be a subspace of R. It can't just be a subset. But if it's a subspace and it is a subset, then it is a subspace of V. Okay, so we have some examples. The zero subspace is a subspace of a line. Okay, so the 0 is itself a subspace, right? This is itself a subspace. You can even be sort of thinking in R2 for this. It's itself a subspace, and it is a subset. It is contained on the line through the origin. So the origin itself is on the line through the origin. Okay, here's another example. A line through the origin, there it is a subspace of the plane through the origin that has that same first vector there. So let's just concoct an example of that, just so we can sort of see it with some numbers. We've got, for example, U could potentially be something like this, 0, 0, 1, and V could be this here, 0, 1, 0. Then if I looked at the plane would be the span of 0, 0, 1 and 0, 1, 0, which means what? All linear combinations. So this P would be the set containing all linear combinations of U and V. There. And that is a plane through the origin. Okay, now we take a look at what I'm going to call L for kind of obvious reasons. And that is, well, I've got, what is this guy here? So that L is going to be the span of 0, 0, 1, like that. Clearly that is linearly independent, and that is going to be the set containing all vectors that look like this. And this here is a line through the origin. Okay, so the dimension of L is 1. The dimension of P is 2. And you can see that the set containing C1, 0, 0, 1 is a subset of the set containing C1, 0, 0, 1 plus C2, 0, 1, 0. Precisely, of course, when C2 is equal to 0. Okay, so we have, in this example, it might be potentially easier to see that then L itself a subspace of R2, or R3 in this case, sorry. L is a subspace of R3. P is a subspace of R3. L is a subset of P. So we have that L is a subspace of P. Okay. I highly recommend, as you've heard me say before, when you see these theorems and statements that apply in every dimension, always a good idea to concoct a 2D or 3D example and sort of see how it's working. And then it makes the theorem, I think, much more obvious to see what's going on. We have just a statement here. If we have two subspaces, V and W, of Rn, and W is a subspace of V, then the dimension of W is less than or equal to the dimension of V, which itself is less than or equal to N. So there's just a statement there about the dimensions. If the two subspaces are equal, then they have the same dimension. Okay, so let's just take an example here. We've got V defined to be all vectors in R4, that's what this is, all vectors in R4 such that these conditions are met. And then W is all vectors in R4 such that these conditions are met. We want to show that W is a subspace of V, and we want to find the dimension of both W and of V. So I'm going to ask myself here, what do the vectors in V look like? Well, I mean, x1 has to be equal to x2. So in some vector, if I pick some vector x, and I tell you that it's in V, then what does it have to look like? Well, it's going to have to look like this. It's going to have four components because we are in R4, and it's going to have to be such that whatever I put here for x1, in order to satisfy this condition that x1 minus x2 is 0, this is going to have to be the same number here. Like this is basically telling you here that x1 has to be equal to x2, and this telling you that x3 has to be equal to x4. Okay, so that means that whatever I have here as x3 is also going to have to be here in the x4 position. Now I can write this differently. I can write that the vectors then, all of them look like this. T times that plus S times that, which looks like this. T, T, S, S. Okay? These are all the vectors. T and S are some real number. And so we have the situation that all these vectors, x1 is equal to x2, and x3 is equal to x4. So V is all of these vectors. So that V is in fact the span of 1, 1, 0, 0 and 0, 0, 1, 1. There's two vectors in there. They're linearly independent. The dimension of V is 2. Okay. All right, V is a subspace of Rn. Sorry, R4. That's what I want to say. Okay, it's that portion of R4 that is spanned by these two vectors. Okay, how about W? What do the vectors in W look like? Okay, I have a vector. If I have X, now I consider X in W, well, X is still going to be X1, X2, X3, X4. However, I have to put some conditions on that. They can't just be any old numbers because I have to have that X1 is equal to X2. So that is going to, that is, then I'm going to say, okay, fine, X1 has to be, X2 has to be equal to X1. Then I'm going to say, oh, X3 has to be equal to X2. And X4 has to be equal to X1. So I just kind of modify this using the constraints here that are being put on. So the vectors in W look like this. Okay. All of the components are equal to one another. They can be anything, but they have to all be equal. So T is some real number. Okay, so that means that W is the span of this guy, 1, 1, 1, like that. Okay, and then there's one linearly independent vector in there. The dimension of W is 1. W is a subspace. W is a subspace of R4. W is a subset of V. W is contained in V. Right, I can see that because why? 1, 1, 1, 1 is 1 times 1, 1, 0, 0 plus 1 times 0, 0, 1, 1. Okay, W is contained in V. So we've got that W is a subspace of V. Okay, another theorem. Here it is. Suppose V is a non-zero subspace and the dimension of V is K. Then you need to have K linearly independent vectors to have a basis for V. A set of K vectors, this should be that span V is a basis for V. A set of less than K vectors cannot span V, and a set of more than K vectors is linearly independent. Okay, so these are relatively straightforward to show, and it is done in the textbook. So rather than do that here, I'm just going to refer you to the textbook for the proof of these 4 things. It's very short. And that's on page 338. Instead, we'll just take a few examples of this in operation. Okay, so I'm going to look here. Show that the vectors 6, 1 and -2, 5 form a basis for R2. Okay, we need 2 vectors. 2 vectors, they need to be linearly independent. They need to span the space, and they need to be linearly independent. So we need to show that V1 and V2 are linearly independent. Okay, so I say here V2, which is equal to -2, 5, is not equal to K times 6 times 1. Why? Because, well, to make the first row correct, K, this number here would imply that K would have to be equal to -1 third, because -1/3 times 6 is -2, and then this row here would imply that K would have to be equal to 5, because 5 times 1 is 5. I mean, this is not compatible. You can't have 2 different numbers there. These so therefore we have that V1 and V2 are linearly independent. and therefore we have that the span of these two things has dimension 2 is equal, the span is equal to R2, and they span R2 and they're linearly independent, and so therefore these two things together, they are a basis for R2. Okay, we're going to do the same thing here. These three guys form a basis for R3. So if we have three linearly independent vectors here, that's all we need to show, because there'll be three of them. The dimension of that is going to be 3, and there's no way of getting a larger dimension than this guy here. Okay, so we just need to show that they're linearly independent. How are we going to do that? Well, one way is to show that the determinant of these three vectors as column vectors in a matrix is not 0. So let's take that approach. So we have three vectors. So here's what I'm thinking. We have three vectors. Need to show they are linearly independent. Okay, so that is if we, I mean, the definition, that is that C1 V1 plus C2 V2 plus C3 V3 equals 0, implies C1 equals C2 equals C3 equals 0. Okay, so instead of doing it, say by the Gaussian elimination model, we could also, using our unifying theorem, realize that actually that is equivalent to showing that the determinant of this matrix 1, 2, 1, 3, 3, 8, 2, 5, 0. I want to show that that determinant is not 0. Okay, so I quickly calculate that determinant. Let's let me just calculate it, wanting to show it's not 0, but it's actually equal to this. That is 3, 5, 8, 0. I'm expanding along the first row. 2, 5, 1, 0. 2, 2, 3, 1, 8. And then that gets me minus 40, plus 15, plus 26. That gets me 1. Okay, so the determinant is not 0. That means the vectors are linearly independent, and the dimension of the span of V1, V2, and V3 is 3. There's 3 linearly independent vectors, and that spans R3, and it's linearly independent. Therefore, these 3 vectors, V1, V2, V3, is a basis. Okay, here's another question, slightly more interesting, a little bit more, this is a little bit more thought-provoking here. We've got some vectors, and there's a claim that they're orthogonal to another vector n. And then it says, why does this mean that V1, V2, and V3 are linearly dependent? Okay, so let's just confirm that they're orthogonal. Or recall that from a while back that we used a dot product to do that. So I'm going to take V1 dot n, and I expect that to be equal to 0. That would tell me that V1 and n are orthogonal. So let's there's V1 dot like that, and that is 4 minus 6 plus 2, and that's 0. Okay, so this means V1 and n are orthogonal. Let's now do the same thing for V2. V2 is 7, 8, 1. Take the dot product again with n, and I'm going to get 7 minus 8 plus 1, also 0. Okay, so V2 and n also perpendicular. Then we have this guy here. That's going to be 0, 1, 1, and I'm going to take the dot product here like that, and I'm going to get 0 minus 1 plus 1. That's also 0. Okay, so I have shown that each one of these vectors, V1, V2, and V3, each one of them is orthogonal to n. Okay, let's write that down. V1, V2, and V3 are all orthogonal to n. Okay, let me start. I mean, these are in 3 dimensions. We are in 3 dimensions here, but let's just imagine a line n. Imagine the line n. There it is. And we know that these vectors are orthogonal. So, for example, there's v1. Now, v2 is going to have to be orthogonal. It could, for example, be here. And I can't draw it well here, but it could also be, for example, sticking out of the page. So all the vectors orthogonal to n, I can see where they are actually. So all vectors orthogonal to n lie on a plane. So you just imagine this line through space and ask yourself, where are all the lines that are orthogonal to a line in 3-dimensional space? And you can see that they all have to lie on a plane for which n is the normal line. Okay. Okay. A plane is 2 dimensions. Okay, so a basis for a basis for a plane only requires 2 vectors to span. You only require 2 vectors to span 2 dimensions. Okay, so I'm saying here that the span of these guys, because they're all on a plane, the span of v1, v2, and v3 is R2, a plane. Okay. However, you see that there's 3 vectors here. So that means that one of these vectors has to be linearly independent. So this number here is 3. 3 vectors is greater than 2, this dimension. Therefore, v1, v2, and v3 are linearly dependent. Okay, well, you will undoubtedly be ecstatic to now see that our unifying theorem is growing. It is growing and growing and growing. I believe that we were up to L the last time this happened, which means we've got 4 new guys here. So all of these statements, if I make any one of these statements, let me just hash this over again. If I make any of these statements, a matrix A is invertible. Then that tells me the row vectors of A form a basis for Rn. It also tells me that the column vectors form a basis for Rn. It tells me that the row vectors span Rn, and it tells me that the column vectors span Rn. So that's what's being added. So for example, I could take a matrix and I could show what doesn't look so related actually. I could take this and say, okay, look, hey, lambda equals 0 is not an eigenvalue of A, and then I can immediately claim that the column vectors form a basis. So now we are up to P, folks. A large number of equivalent statements. So again, my strong recommendation is to, I don't know, write this out once a day. Try to write out as many of them as you can and then see which one you're missing and just sort of keep going so that when you're doing a problem and you're trying to solve a problem and something comes up that you want, maybe you want to show this. Maybe that's what you want to show for some reason, or you need to know, is this the case? Maybe it's hard to or time consuming to calculate directly, and you're like, you know what? I've already been told, for example, I don't know, that that matrix is invertible. So then I can just refer to that and then claim this. So you want to be able to use these things to go back and forth. And I just know how happy you are now that there's 4 more. 4 more items here in our unifying theorem. Okay, that is all for today, and I will be back with section 7.3 shortly. Thank you. Bye.